Okay, in the previous video, we took a look at how we can calculate the Laplace transform of a constant function. So now let's try some more complicated examples. So in part A, we want to calculate the Laplace transform of the function g of t, which in this case is e to the 3t. And so again, the definition of the Laplace transform tells us that this is going to equal the integral from 0 to infinity of e to the minus st times our function, which in this case is e to the 3t dt. And so let's write this again as the limit as n goes to infinity of e to the, I'm going to write this as 3 minus st dt. So I just combined the exponential terms inside the integral. And then we integrate this using substitution. And this is going to work out to 1 over 3 minus s e to the 3 minus s times t, all to the 0 over n. 0 up to n. And we're taking the limit now as that upper limit goes to infinity. And so what we got is now we're going to plug in each of these values in for t, because s we're treating like a constant. So I could just actually go ahead and pull out this 1 over 3 minus s, because it doesn't depend on t. And then we're going to multiply this by what I get when I plug in the upper limit, and then subtract what I get when I plug in 0, which is going to be e to the 0. And so again, we have this improper integral, and it may converge or it may diverge. And so what we need is this piece over here. As long as we have e to a negative power, which is getting more and more and more large in a negative sense, we know that that's going to head to 0. So as long as we make 3 minus s a negative number, then that's going to work. So in other words, as long as s is bigger than 3, that first term is going to go to 0. So we just figured out what our domain is. So now, as long as s is bigger than 3, we're going to get 1 over 3 minus s. And what's left inside here is, well, as long as s is bigger than 3, that's going to be, the first piece is going to be 0, and then the second piece is minus 1, or subtracting 1. So simplifying all of this, what we can see is the Laplace transform of e to the 3t is 1 over s minus 3, as long as s is bigger than 3. So that's our solution for the first problem. Okay, and you can kind of think to yourself, well, what would happen if I had e to the 8t and I took the Laplace transform of e to the 8t? You can convince yourself that yes, you would actually get 1 over s minus 8 as long as s is bigger than 8. Okay, so let's check out part B, which is now asking us to calculate the Laplace transform of the function t. So by definition, that's going to be the integral from 0 to infinity of e to the minus st times our function, which in this case is t. And we integrate that with respect to t. So to integrate this, we would need to use integration by parts, where, for example, I could set u equal to t and v prime equal e to the minus st, which would give us u prime is equal to 1 and v is equal to minus 1 over s e to the minus st. And so if I do integration by parts on that, then I would get uv, which is going to give me minus t over s, e to the minus st, times 1 over s e to the minus st. And so if I do integration by parts on that, then I would get uv, which is going to give me minus t over s, e to the minus st, times 1 over s, e to the minus st. And so if I do integration by parts on that, then I would get u v, which is going to give me minus t over s, times e to the minus s t, and then we subtract from that the integral of u prime times v. So because I have this negative sign over here, I can combine it with the negative sign from the integration by parts. So I'm going to add to this the integral from 0 to infinity of minus 1 over s times e to the minus st dt. And actually, I just remembered I put the negative sign in front. So this negative combined with the negative from integration by parts to get a positive there. And so now we're going to take the limit as the upper limit n goes to infinity of minus t over s e to the minus st. And then integrating again, we're going to get another negative 1 over s multiple. So I'm going to get a minus 1 over s squared e to the minus st. And we integrate that from 0 up to n. So when we plug in positive, or when we plug in our upper limit, which is n in place of t, I'm going to get minus n over s e to the minus n times s. And then when I plug it into the other term, we're going to get 1 over s squared e to the minus n times s. And we're taking the limit as n goes to infinity. So that would be our upper limit, what we get when we evaluate the upper limit, and then we could subtract what we get when we evaluate this at 0, which is going to be 0 when I plug in 0 over here, and from the second part we're going to get a minus 1 over s squared times e to the 0, which is 1. And what we want to do is make sense out of this limit. And we want to figure out for what values of s is this limit going to converge. And so one of these we've seen quite pretty much in all of the previous examples, and that is as long as s is positive, then that piece is going to go to 0 because this power up here is going to become a large negative number. And for the first piece, it's a little bit more complicated because when we're taking a look at this, we actually have, as n goes to infinity, that part goes to infinity, and that part's going to go to 0 as long as s is positive. So we have something heading towards infinity times something which is heading towards 0. And so let me just quickly say that if you wanted to evaluate this limit, then we can think of this as e to the minus n times s, all divided by the reciprocal of the multiple that we actually have in front. And now using this and L'Hopital's rule, you can convince yourself that this also goes to 0. And the short answer is the rate at which e is heading to 0 is faster than the rate at which n is going to infinity. So this term dominates this term over here, and altogether this product is going to head to 0. So as long as s is a positive number, then both of these limits are going to converge to 0. And so after all of that, therefore, we get 0 minus a minus 1 over s squared. So in other words, we get 0 plus 1 over s squared. So our Laplace transform, therefore, is f of s is equal to 1 over s squared as long as we have the condition that s is greater than 0.